Okay, good morning, everyone. Normally you hear me and you can see me, perfect. And the recording is ongoing. So welcome everyone to this second session of the Code of the Month public webinar. Today we have the great pleasure to welcome the Center of Excellence RAISE. We will have the speaker Xin Liu and Erei Inang. Unfortunately, Maurice Riedel will not be able to attend today, to speak today, but he prepared a kindly video. So we will share with you this video as a first part of this webinar, and then we will have the talks from Xin and Erei. And there will be some time for questions at the end of the presentations for this 1 hour public webinar. If you have questions, you can, during the presentations, already write them in the chat or raise your hand and we will interact with you after the talks. But first, let's start with the video. Allow me to share it. Okay.
Yeah, welcome everyone. Also from my side, my name is Morris, and I think many of you know me already from activities around CASTIEL or the EuroCC project. I'm the head of the National Competence Center in Iceland, and also partly still working a little bit in the UAIF Supercomputing Center. So today we talk about the Center of Excellence RAISE and its unique AI framework. And I would also use this opportunity really to phrase this a little bit as a call for collaboration, because every one of you listening here basically is invited to collaborate with us, and we will talk about it. So I apologize up front when I cannot be there directly live on the call. It probably means I'm getting a father again. So in this sense, I had another reason to not show up, but I have a recording for you that hopefully will help you equally. So from the agenda point of view, we have a very good teamwork in CoE RAISE. So we have 3 speakers. I'm starting a little bit warming up with some challenges and frustrations that really motivate the idea of this unique AI framework. And then I will provide a little bit an overview of all the different solutions. Apparently, this is a project running for 2.5 years already, so we cannot possibly put that all in 40 minutes. Hence, we pick several different pieces here that really highlight these solutions and pick a couple of pieces out of it. Also, I will introduce a little bit about the collaboration initiative that we have already started with some of the NCCs maybe listening here today, and also some of the EuroHPC hosting sites. In order to pick several different pieces that matter here for the collaboration part, we will talk a little bit more about LAMEC, and this will be a talk given by my colleague Xin Liu from the UAIF Supercomputing Center that will provide some of the solutions that really simplify AI and HPC access with job script generators and so forth. And because many of the industry uptakes that we see in HPC are usually in the area of CFD, computational fluid dynamics, we will also show you a little bit how an AI for HPC library, part of this framework, will also basically enable users to really do their first steps into AI very quickly by basically having already ready to run solutions, so to speak. We have lots of time for discussions afterwards. And up front, I also want to share with you some information. RAISE, I think here you see, for instance, the RAISE website. Obviously, there are lots of information about the RAISE projects, our use cases, research, and so forth. And also the unique AI framework would take several hours to go into every little detail. So we have a unique website for you under this particular URL. So it's quite interactive. It's quite nice, explaining you a lot about it. So I would encourage you to also go to this RAISE maybe after this event. So starting a little bit with the idea why we need such a framework, and this starts basically out of frustration when we basically going for CoE RAISE 3 years ago with a proposal. And basically, we work in the supercomputing center, perhaps like me, 20 years now. We have seen many frustrations of the job scripts again and again. And with AI at scale, it's even much more harder. When I talk about frustrations, is usually thinking about what is the best distributed deep learning tool for training now available. There are many different of these logos. I'm sure you have seen several of them. So what scales best, or what is basically hindering us in scaling up? Are there any limits? Lots of questions where nobody is really sure about. And basically also, we want to have better models. We heard a little bit about hyperparameter optimization and neural architecture search and these topics, but how we do this and how we can get users from Google Colab environments they will know actually also to our HPC systems, which are quite frankly much more complicated. So when I want to have an example of a batch job script, what happened in my research group and what I have seen in Jülich since 20 years, people send around widely job scripts that work 1 week and the next week it will not work. And there's a problem with some of the modules. And the tough nut, as I would summarize it here in this, is really this, what you see here, the different stages, the different versions that you see here in all these different libraries, right? So the general idea of the job script might be okay, but you always need to know what are the little details really of all these different modules you want to use. And this is basically getting into an increased complexity. There will be more and more of the heterogeneous hardware we face, NVIDIA and AMD GPUs, like in Lumi, for instance. And there will be more your HPC JU hosting sites available. So we need to often more porting our applications than in the past for computing time. So this all was basically a driver of the CoE RAISE project. And you see here we have some compute and data-driven use cases on the left hand, beginning from the project on board. And what we did was really doing HPC and AI methods in the sense of really using cutting-edge deep learning models. You see many of them here, transformer models, very popular, autoencoders. Basically, we have here also graph neural networks, a very new material. On top of others that we have seen as convolutional neural networks that really use HPC at scale. And the red blocks, by the way, are just new elements that have been recently added or removed. But you see, really, we have quite an experience also in the low-level AI algorithms we use in all the different use cases. And by doing this now since 2.5 years, we come to something we call the so-called unique AI framework. And this stands essentially on the right-hand side summarized with the idea that we had different hardware infrastructures. We looked at different software infrastructures of what are the tools in all of these different computing-driven and data-driven use cases to find more or less common requirements to shape this unique AI framework. So basically, in a nutshell, you would say it's not, again, another TensorFlow. It's not another PyTorch or Horovod. It's just basically a combination of the right set of tools that we have proven to scale and in the right versions. And with this, we have an idea that you see a little bit here on the layers. Again, there's a website for it and also a paper if you remember, where all the different blocks A, B, C, D, etc. are explained. But you see, we also think that the use cases we have in the project is just one part. The domain-specific CoE use cases, also other center of excellences, the national competence centers and their industrial use cases, digital twins, they all can benefit from it. On the other hand, we see the other part of the ecosystem where we live in. So that means basically the EuroHPC JU hosting sites, with Jupyter, the exascale system coming along next year. Then we see the EU HPC systems, which might be not hosting sites, but still very relevant, especially for onboarding users in AI. And of course, not forget about the future and innovative hardware architectures, prototype architectures like ARM systems and so on. We also do a lot in quantum computing, which is not so much part of this talk, but something where we basically focus on is essentially this part here in the middle, where you see the framework and the different tool sets we have already described, TensorFlow, PyTorch. If you want to do distributed deep learning, you have to add Horovod or PyTorch DDP. More recently, also DeepSpeed is available. And we have hyperparameter optimization to make better models, better parameters. We have RayTune, Optune, and Deep Hyper tested. So all of them basically work well, and we confirm that they can run on HPC and will be part of the framework. But of course, you see also other parts like simplify access with interactive Jupyter notebooks and kernels at scale, application workflows with Apache Airflow. And one of the elements which I will basically link to a little bit is the LAMIC API that we have basically created to make it really easy for users, and is one heart of it, which really means JavaScript generators and an API to really simplify HPC. So basically, to bring you this idea of the framework quickly into mind, without going in all the different details, I refer again to the website. I will just pick some highlights on the mindset, skill set, and tool set level now. And when we look on the mindset, it's often clear that AI communities which not previously used HPC are often also frustrated with the idea of how to use HPC, much more complicated than people think. Batch scripts, you have to know the right modules, as we said. So here we started with a LAMIC API that will be basically presented by Dr. Xin Liu from the Uli Supercomputing Center, and LAMIC stands, by the way, for Load AI Modules, Environments, and Containers, where we have basically looked at different job scripts and all the different systems we have, Deep, Eureka, Juvels, but also Vega, Lumi, and so on, and have basically created a job script generator that we currently extend significantly to new EuroHPC JU hosting sites. For instance, Vega is now supported, and I think Sin will talk about it, but it helps us to generate then automatically this tough nut I was alluding to and keep track of the changes, which are really the devil in the detail. You see here Nickel, NVIDIA libraries, CUDA, very specific for all the different systems. So with this, we address really this 2 to 3 days that usually people spend to get this basically this up and running without any automated setup, and they do that manually. So here we help basically with lots of time gains, and it's already live. You can use it yourself, and will be also one cornerstone of collaboration. We have also other elements in the unique AI framework, basically beyond even the simplifying of access with generating these job scripts. We have, of course, also other tools that should make it simpler for people that want to adopt AI at scale. Of course, we have the UAIF components itself, but to go beyond this in the different disciplines or to use specific AI methods like graph neural networks, you see here in a CERN use case with machine learning particle flow, or here with the AI for SIM driven by Atos and others. So here you basically get a Git repository where you have already interesting open source data sets and also the scripts that you basically require to get started. And this also includes, for instance, a very interesting topic we have also as one of the major parts in RAISE, which is here this interesting coupler, basically between traditional, let's say, simulations or simulation sciences, which are simulations usually based on numerical methods that are in turn based on physical laws. And then combining this with deep learning and so on is a new idea with surrogate modeling and so on, which is quite an interesting topic. And there's a Git repository. All of this is also on our website. So more on another part of tool, as I was alluding to in the beginning, is also the AI for HPC for CFD researchers, which will be given by Iray Ineng from the Uli Supercomputing Center later. Then on the skill set level, using AI at scale is clear that this is not so easy, just throwing Horrorwhat on it. And there are different reasons for it that I can go into all details again. But one is the problem of large batch sizes. You see this quite nicely. While the speed up is still there, we can use here 2000 GPUs in parallel, that's fine. We see a significantly drop, not only in efficiency, but also in the training error, right? That is basically increasing. So that means we have quite a nice architecture with the Juvels Boost here, for example, with A100s, but is it efficient and useful to scale is a matter that is not always very clear. And you see also, if it is a tool problem or not, you can see here quite nicely that the tools PyTorch, GDP, or Horrorwhat, when you use, for instance, the DALI data loader, they have almost the same performance. Again, the efficiency drops significantly by the number of GPUs you use. In other words, the more GPUs we use, we have to increase the batch size. And with this increased large batch size, we also actually lose the validation accuracy. It's called the problem of large batch sizes, and there are several curves for it that we do in the project. But there's another big important part in RAISE, which is this distributed hypertuning. We use RayTune a lot there, in turn using different trials with different, let's say, neural architecture parts and fine-tuning of parameters. I don't go here in the detail, but it is a CERN use case where we, for instance, could drop the validation loss by 44% just using hyperparameter tuning. And this is, of course, quite nice results that many people can sell. So we can not only speed up the training with distributed deep learning, we can also make better models with HPC by using hyperparameter tuning. So that is kind of a selling argument for you maybe to collaborate with us, but we have more to offer. And you see here a little bit the overview. What we envisage is that this job script generator, this repository behind it, can become a community effort really along our European HPC community. Everything is open source. We are happy to share. NCC Iceland, Germany, and a couple of others have already actually shown quite some interest in working with us together. We aim to have not only, of course, Vega and the Jülich systems, but much more HPC systems supported in the future, so that we all can basically benefit from the knowledge we have in the unique AI framework. And that's all I wanted to share with you now. I think now it's a time for Xin. So thank you very much for your attention, and feel free to basically contact us later. Talk to you soon.
Okay, so thank you, Maurice, for this video. So now I will make the new presenter. So you should be able to present now, Xin.
Yes, thank you. So can you see my screen?
Yes.
Okay, great. So now, thank you everyone for coming to the webinar. So now I will present our tool that we developed. It's called LAMIC, loads AI modules, environment, and containers. So the motivation is, as Maurice just described, the common frustration that is experienced by a lot of us. So the HPC systems, they rely heavily on the software modules that you load. So you have to struggle a lot to get the correct start script. And also you have to update your start script in a timely manner, because sometimes with the software updates, it can easily break the software dependencies. And the goal of our LAMIC tool is to simplify the setup of the components. So in RAISE, we have a lot of partners. We're a lot of power users of HPC and AI. They will provide us with some start scripts in a timely manner. And so, for example, this is a repository that we collected a lot of those scripts, and we just need to think about how can we make the best use of those scripts for people who are not so familiar with the system. So the LAMIC API, the idea is to let the users input the software they want to use, and also the API will fetch the correct module setup from the scripts that we already collected. It also sets default values for workload managers like Slurm. And it's not only a command line tool, but also a web page tool. So if you like, you can visit our open source repository for the LAMIC tool, and it is also hosted on web page on Jülich site. So right now I will show you a video to give you a demonstration of how the LAMIC tool works. So you are suppose the user is already on HPC system. In this case, it is Eureka. So you input the software that you want to load, that is DDP, the account and number of nodes. So you use our command line tool, give the inputs, and then it will generate the job scripts that you need. So when you open the job script, you will see that it sets the Slurm options and loads the correct module, and exports correct environment variables, and also loads the launch comment for DDP. So this is a very simple DDP script that you can test. Now I submit the job with the job script that is just generated. And now the job is submitted and it runs on the system. Yeah, so now the job is running, and you successfully, very easily get the correct job scripts for running the job. So our LAMIC tool is also supported on a web page that is hosted on Jülich site. So if you see for this web page, you can select the system that you like. So we not only support the systems on Jülich site, but also on Lumi and Vega, and we are working extensively to expand our support on different systems and software. So select the system and the partition you want to use, and also the software you want to use. Inputs, for example, your Python file you want to run, specify the number of nodes and also the account. So now it will generate the start scripts you need, so you can just copy and paste and use it for your job. Yeah, so that is my presentation. I hope it raised some of your interest, and yeah, so feel free to explore the webpage that I put in the presentation. And also for our upcoming plans, we are trying to work to extend the support on different sites and also implement automated testing. So so to make sure our information, the module dependencies are up to date, and also extend the LAMIX support for containers, Omnix format, and enable reusability of existing AI models. So thank you very much.
Thank you, Xin. So I'm making AI presenter.
Hello, everyone. I hope you can hear me.
Yes.
Let me see how I can share my screen.
It's at the top of the module sharing. And you can click on the play logo to show your screen. And you can select which screen to share.
Well, at the moment, I think it's broken. Nothing works. Let me relog.
Okay.
Okay, that doesn't work too.
Do you see the module with a sharing part?
I think Ira is trying to relog.
Okay.
Yeah.
Okay, for the moment we still see him, but yeah.
Yeah, he's back now.
Okay, could you give me the rights again?
Yes.
I hope this works now.
Yes, and we can see your screen.
Oh, okay. I hope you can see this one now. This is the slides.
Yes, we can see the slide.
Okay, sorry for the delay. My name is Erai. I would like to promote AI for HPC, which is part of Unique AI Framework. It could be, as Morris said, it could be interesting for CFD people, but could be interested for any data-driven project that you have. Okay, let's start. So what is AI for HPC? We think that as a triangle, in each edge, we have a different component. We have AI on the top and CFD and HPC on the bottom, left and right. It's an open source library, actually, which combines all these three aspects together. For instance, if you are working on a CFD code and if you have an access to HPC and if you are wondering if you can implement an AI aspect to your CFD framework, you can actually start with this AI for HPC. Or in other way, if you are working with AI and if you have an access to HPC, if you want to train safety datasets or any data-driven project datasets, whatever you have, you can. You don't have to worry about it because you can immediately start developing from starting with our framework. We have a good documentation we can go to this link. It's in the read the docs, what we can do. But quickly telling what is inside is that we have a lot of pre-processing routines in AI for HPC. This means that in data-driven projects, you have different datas and you probably have different dimensions for each data sets. We have a lot of examples how to pre-process this data, so it becomes an input to this machine learning architecture, for instance. We have identified a lot of different machine learning architectures that are useful for the CFD. One example could be like in autoencoder, or another example could be like a super resolution. So you don't have to like dig it in the internet or in the books. You can immediately see how this super resolution is being implemented to train, for instance, for its safety dataset. Of course, this is the most important part, is the HPC optimizations, which I will come later on. If you pull for instance, a repository, let's say a framework, PyTorch or TensorFlow that you want to train with AI, and if you find it that so there are some examples with the HPCs, you will immediately run to a problem that it will be pretty slow. So each HPC has its own optimizations that we have collected, and then we have made it available for anyone who wants to pull our repository. And the most importantly, the CFD or any data-driven project, you can actually plot these data. You can make nice images. So we have some examples how to post-process this trained data set or compare it with trained and original data set, etc. We have a benchmarking suite. If you want to test the limits, for instance, for your HPC, I will come to that, but we can actually scale this code to pretty large numbers of GPUs. And another important part is the hyperparameter optimization. That training alone, you will come up to different hyperparameters that you need to optimize to get the best accuracy, we have some examples how to do this in automatic manner. This is the source code. You can actually access this from the read the docs, but here's also the link. So feel free to check it out. Okay, why do we need HPCs actually for training? And for the safety dataset, we have first started with the autoencoders. We have implemented that using one GPU, and we found out that one epoch to train a safety dataset using the autoencoders would take like 2 hours. And my colleague here, Rakesh, Dr. Rakesh Sarma, has shown that a converged architecture will probably need more than 1,000 epochs. Plus, you need to do a lot of hyperparameter optimizations. So this will take months or a year to actually finish this. The solution is, of course, to use the HPCs, but you cannot just hope the HPC to solve all your problems. So where to start is actually, you can just pull our repository and then start it. In our repository, we have shown an example of this distributed training. This is a parallelization approach where you have a huge data set. On the right-hand side, you have this picture. On top, you have this turbulent boundary layer TBL dataset. For instance, you have terabytes of data. If you pass it through one GPU, it will take years. What this does is that this splits this dataset to different GPUs, which in this case workers. And each worker or each GPU will have identical machine learning architecture. It will do its own backpropagation, and then it will transfer the computed gradients and weights to a host. You will do a averaging of the gradients and weights, and then it will send it back to the worker. This communication, you can, in this AI for HPC, you can select 3 options. One of them is the NVIDIA's collective communication library, NCCL, or the Radeon part for AMD. You can also use MPI, but with CUDA support, or from Facebook Glue, which is at the moment experimental. Well, it works. Of course, as Morris said, we have problems on the mini batch sizes approach that you have to take care, that I will come to it. And well, we don't have to reinvent the wheels, we reinvent the fire. In this case, there are a lot of frameworks that does this kind of distributed data parallelism approach. For instance, PyTorch has its own library. We have Horoword, we have DeepSpeed, and we have internally this Heat from Helmholtz. These have already have a lot of implementations that we have based AI for HPC on top of it. And also, as a CoE RAISE project, we have access to different hardwares. So we have tested AI for HPC in very different hardwares. So we are confident that it is a quite scaling framework. And well, we are constantly developing. So anytime we have an access to a new HPC, we are testing AI for HPC framework, how it is doing, how we can improve the HPC optimizations, etc. Let's check the performance. Well, we did a scaling from 4 GPUs to the complete 3,664 GPUs on Jules Booster in Yuli. And you see the red line is the one that we achieve, is a speed up, and the black line is the ideal one. So we have a very high efficiency even with the complete system. You will probably see some Verser results later on in this presentation to explain that this is a synthetic benchmark where we have a synthetic dataset instead of the CFD dataset. The dataset size is the same, but it's just disables the input output and generates this CFD dataset synthetically. But this is the expected scaling performance of AI for HPC. Of course, in AI for HPC, we have tested different GPUs too, and we are confident that AI for HPC is compatible for various hardware and middleware. You will see, depending on the type of the GPU or the manufacturer of the GPU, we have a different performance. But the good thing is that the communication between the GPUs or the scaling performance remains the same. So you can use AI for HPC on different hardwares, and you will not lose scaling performance. Of course, you will lose the per GPU performance. We also started testing H100s as an experimental. So we are constantly testing different hard and middlewares, and we are updating our repository depending on what we can find. This is a framework comparison. So I showed you we have 4 frameworks. We have this is a very small test on Eureka in Yuli, up to 64 GPUs. The only thing that is important in this plot is that even though you have the same very similar codes that does similar parallelization, internally they're a little bit different. For instance, if you check the training error on the right top side, depending on the framework that you choose, you will have a different training error or the accuracy. We have implemented all of them in the AI for HPC, so it's better to test different frameworks depending on your code and see what kind of training error you achieve. But it's quite nice that if you just pull the AI for HPC with one click, you can just modify this framework from Heat, for instance, to Horoword. Some implementations optimizations worth to mention here is that we have a special data loader, multiple access data loader that deals with irregular data shapes. So you will see that if you have a data-driven project and if you have a very various dataset sizes, the padding is not a solution all the time. Okay, you can do it, but if you have very different dataset sizes, so we have some ideas how to tackle with this problem. For memory issues, we have automatic way to change the precision, or we have different approaches to actually reduce the precision or increase the precision depending on your problem. Well, you can, okay, this is not written here, but for increased precision definition could be important for safety data sets if you have, for instance, a scalar that has a wide length scales, for instance. If you, that could be a velocity field could be a good example that then you want a higher precision, for instance. We have adaptive summation algorithm that I will come to it later on. We have deterministic test runs, different training errors that are specifically designed for safety problems, because in the training error, it's not like the standard machine learning accuracy. Instead of something is right and wrong, you have now vector fields that should match the original field. We have some examples on that, and we have gradient accumulation and different profilers. So at the end, if you pull, for instance, PyTorch, and then you modify PyTorch that would run on your HPC, for instance, in this case, I think this was an Eureka DC, again, you will have this red line. In AI for HPC, with our optimizations, we achieve this blue line, which is actually 10 times faster. I will come to why the efficiency is a little bit is a lot lower than the one that I showed previously. But the important part is that with the optimization, our efficiency is at the same as the standard, so we don't lose any efficiency. Okay, so why is like the efficiency is lower when we have this turbulent boundary layer dataset? This is quite simple. This TBL dataset is 8.3 terabytes, but this distributed data parallelism approach is that it just splits the dataset to different GPUs. If you go a lot of GPUs, this means that every GPU would have less data per GPU. So this means that you will have another issue that for smaller data sets, constantly giving more workers or more GPUs would not scale the code at all. So the number of the GPUs and the dataset size is linked somehow. So on the right-hand side, you see our tests, our profiling tests that you can see from 4 GPUs on the pie charts from the top row, 64 GPUs from the bottom row. You see the communication is red. It increases tremendously because you will not have any data set to actually do any backpropagation. So we tested this with 10 times larger data set, what would happen? For instance, for 64 GPUs, if you had 83 terabyte, you would have much better efficiencies. So this is clearly a sign that even with 64 GPUs, you will need more than 100 terabyte dataset size. And of course, this is the most important part, is to deal this large mini batch sizes. If you imagine, if you go to an exascale system, if you have a huge data set, let's say that petabyte of data set, and you want to use like 1024 GPUs for the training. And if you select a micro batch, which is the batch size per GPU to 1, you will end up with a batch size of 1024 minimum. So this is problematic because you cannot go to low batch sizes. Then you have to play around different hyperparameters. For this, our HBO cert comes to play. For the CFD dataset, we have found out that the learning rate is the one that affects the accuracy the most. So playing with the learning rate with this high batch size made much sense. So we have implemented an AI for HPC to different methods. We can actually scale the learning rate with the number of workers. This is like in the paper, very nicely done, but the problem is that you have to be lucky with the starting learning rate. For instance, 1 GPU learning rate times the 1024. If you are lucky, your accuracy will drop, but if you start with the wrong learning rate, you might always end up in different accuracies. So this is a lot of try and error. It's very simple to implement. We have also implemented adaptive summation algorithm. This is harder to implement. This is actually for the gradient computations, gradient averaging. The idea is that the problem becomes independent of the given learning rates. So whatever you given the initial learning rate, you would have similar training error at the end. On the right-hand side, I can show you what I mean by that. For instance, if you just have a learning rate and the same problem that I showed you previously of 0.001, you would have this red line if you increase your GPUs. And because we were lucky, the blue line is the one that we scaled. So you immediately see that the training error is factor of 5 lower when you just scale the learning rate. But if you don't want to deal with this, you can just enable this adaptive summation algorithm from AI for HPC. Then you will have this green line. And 64 GPUs is slightly worse than the blue line. I agree on that, but it is a very simple fix for a large batch size problem. So initial results before coming to an end is like we trained this turbulent boundary layer, and we wanted to do a super resolution. Our motivation was that. So we wanted to recover the velocity fields from 5 times coarser grid with a model called convolutional defiltering model that we developed here. And you see in the right-hand side, you have 3 contours. The first contour is the original field. The second contour is the 5 times coarse velocity field. Sorry, the middle one, if you give it as an input, this model will give you an output on the right-hand side. And if you extract this red line to line plots, for instance, in the middle, you see the original one is the black dashed line, and it's very well hidden behind the blue straight line. So the input here is actually the coarse grid, which is this red line. And this model will effectively give you almost perfect reconstructions of this via the super resolution technique. The bottom line plot is for the gradient of the velocity. You see immediately that this model, this convolutional defiltering model, can actually reproduce this gradients of the velocity field almost in perfect way. So you can immediately start doing this kind of study by just pulling AI for HPC and training your data set. A few remarks. AI for HPC is first step to combine these 3. We have a complete package. So you can just go to this link, pull it, and then train your data set. We have also some exemplary data sets inside that you can just use to see what's going on. Of course, this input-output is problematic. It will always be problematic in the HPC sense. But other than that, we are confident that with right conditions, you would have a great scaling performance using AI for HPC. The most important part is that we are constantly developing AI for HPC with the experts all around the world. And I would like to also mention that we have written all the time the safety, but AI for HPC could also be used for data-driven projects. Well, that's it for the AI for HPC promotion. Thank you for your attention. I give back to Shin.
Okay. Shin, do you need to have presenter mode? Or
No, I don't. I don't. It's that's all for our presentation.
okay. So as the presentations are now done, I will just stop the recording before starting the Q&A session. So